Hi everyone, this is Dr. Sandeep, working as Associate Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss about the iron carbide phase diagram. So till now we have seen different types of phase diagrams, how to draw the phase diagrams and how to draw the cooling curves. All these things we have drawn with the help of the Gibbs phase rule. Now the most important part of the phase diagrams is the iron carbide phase diagram. So in this we will see what are the importance of the iron carbide phase diagram and what is the conversions of these iron to the iron carbide and how many phases are present in the phase diagram, and also the melting temperatures also we can find out with the help of these phase diagram for the case of iron and iron carbide phase diagram. Now coming to the iron carbide phase diagram, so what is the importance? What does it infer from these phase diagram means the iron carbide phase diagram is a map of the temperature at which different phases change occur on very slow heating and cooling in relation to carbon. So what are the changes happening inside this the carbon phase diagram during the process of slow cooling or slow heating process? So that we'll get the information from this iron carbide phase diagram. So what is happening here? What are the change of phase? How the change are being carried out during the transformation of slow heating or slow cooling process. So the information of change of phase we'll get from the iron carbide phase diagram. So this is again the graphical representation of these phase diagram along the x and y axis. So x axis refers to the composition and y axis refers to the temperature. And what does this iron carbon phase diagram will show? So this iron carbon diagram will show us the type of alloys formed under very slow cooling. So what are the different types of alloys are also being formed during the slow cooling process that also can be inferred from this phase diagram. So during the conversion from iron to iron carbide, and during this cooling process, what are the new type of alloys are being formed can be observed with the help of this phase diagram. So that is one of the point which is observed in this iron carbide phase diagram. Next one, proper heat treatment temperature. So at what temperature we have to heat the material? So what are the melting temperatures or what is the casting temperatures can be inferred again from the help of the phase diagram. So that is the second point we can get from the iron carbon phase diagram. And the third one is how the properties of steel and the cast iron are radically changing by the heat treatment process. So what are the change in properties? So from one state or one phase to other phase, there is a lot of change in the properties, whether it is a chemical or physical or mechanical property. So these properties can also be studied with the help of this phase diagram. For the steels and the cast irons, these can be radically changed with the help of the heat treatment process. So if you go on increasing the temperature or you are reducing the temperature, what is happening here? There may be some changes in the properties of the steel as well as the cast iron. So these can also be calculated with the help of the iron carbon phase diagram. Now the other thing is the equilibrium phase diagram. So what is the equilibrium phase diagram? So in the name itself we have equilibria. So equilibrium phase diagram is it gives a relation between the phases which are in equilibrium in a system as a function of temperature, pressure and the composition. So that is very important. So what does this equilibrium phase diagram is giving means? So this gives us a relation between the phases which are in equilibrium. So some phases may be in different states, but this equilibrium phase diagram gives the information about the phases which are in equilibrium. Okay, and these equilibrium phases are a system which is a functions of the three control parameters. So what are the three control parameters here? We have the composition, pressure as well as the temperature. So which are a function of these three parameters will give us the information about the equilibrium phases. Now steels are alloys of iron, that is the Fe. So iron is called as the Fe, that is the symbol, and the carbon. Now this FeC, that means the iron carbon. So FeC is nothing but the iron carbon phase diagram is fairly complex one. Why it is fairly complex one means we consider only the steel part of the diagram. We are not considering beyond the steel part. Why? Because beyond the steel part, it will convert to the graphite. That is the complete 100% of carbon. So we are not considering 100% of carbon because after that composition percentage, it is not under steel. That's why FeC3 means, that means this iron is converting into carbon. That's why it's called Fe3. Okay, so Fe3C, that means the iron to iron carbide. So what is the percentage of the composition of the carbon? Up to this grade we have to see. So beyond that again you will get the graphite. So we are not considering the graphite. That's why it is a complex type of things. If you consider any type of, if we compare with any type of phase diagram with the iron carbide phase diagram. So this iron carbide phase diagram is very complex because it is having two sections in this phase diagram. So other compositions will have only a single thing. Directly we can take up to 0 to 100% and we can get the phases and we get the temperatures of all the casting temperatures. But in case of this iron carbon phase diagram, what is happening? In this case, we have two different phases. Okay, so one phase is from Fe to Fe3, that is the up to cementite, up to carbide, iron carbide. And after crossing the composition weight percentage, it will convert completely to the graphite. So that we are not considering into this case. That's why we are considering only the steel part, up to steel part only. Why? Because we are using these steels for the general application. So up to the steel part of the diagram only we are taking these things. So what is the composition percentage here? 6.67 weight percentage of carbon we are taking consideration. So beyond that we are not considering the phase diagram. That's why while drawing the phase diagram of the iron carbon phase diagram, so we have to restrict the composition percentage up to 6.6%, 6.67% of carbon only. But when you compare with the other phase diagrams, what is happening? We are taking up to 100%. So up to 100%, there is no change. Okay. But in this case, we are getting two different parts here. Two parts are there in this phase diagram. So up to steels only we are considering, that is up to 6.67 weight percentage of the carbon. Now the other forms of the pure iron are, so what is happening here? Allotropic form. So what is the allotropic form means? Which is having a different types of crystal structures. So during the heat treatment process, the crystal structure, the structure of the pure iron can be changed into different structures. So how it is being changing, we'll see now. So pure iron, when you heat, so it experiences two changes in the crystal structure. So whenever you heat the pure iron, we can experience, or it can experiences the changes in the crystal structure. So how these changes are happening in the crystal structure during the heating process before the melting state. So before the melting state, whatever the pure iron is there, it will experience two changes in the crystal structure while heating. So all these allotropic changes are apparent along with the left vertical axis of the phase diagram. So allotropic changes are nothing but during the heating process of the pure iron, it is changing its crystal structure. Okay, at one state you have one type of crystal structure, another state you have another type of crystal structure. Again, it will come back to the original thing. So like this, you have the different types of crystal structures are being formed before the melting state of this pure iron. So all this can be reflected on the left vertical axis of the phase diagram and how it is being changing. If you see this figure, you can observe clearly. So before it was in a liquid state, slowly it goes to BCC, next FCC, and again to BCC. So this is the allotropic form of the changes of the crystal structure during the heating process. So before the melting state of the pure iron, so this pure iron will experience two changes or different changes of the crystal structure. So at room temperature or at the stable form, which is called as a ferrite or alpha iron, or the alpha iron, which is having a BCC type of crystal structure. Now we are heating this pure iron. Okay, so during this pure iron heating process, initial state is what? At room temperature, at normal temperature. So this pure iron is called as a ferrite. So at pure room temperature, which is at stable condition, which is called as a ferrite, or the alpha iron, which is having a BCC type of crystal structure. So this we have to remember very carefully. At the initial state or at room temperature, whatever the pure iron is there, this pure iron has an BCC type of crystal structure, and this is also called as an alpha iron, which is at the stable state condition, which is called as a ferrite. Ferrite or alpha iron at room temperature, normal temperature, which has a BCC type, that is a body centered cubic structure type of thing, you can observe for this pure iron when it is at room temperature, and it is called as a ferrite type of iron alloy. Next, slowly, so you can represent along the left vertical axis for the phase diagram. This is the ferromagnet, that is the alpha, which is having the BCC type of crystal structure. So this is the first thing what you can observe in this case. So this is called as a 1. We'll represent it as 1. So this is at room temperature, which is having a BCC type of crystal structure. Now, slowly this ferrite, whatever the alpha iron is there, which is called as a ferrite, it will experience a polymorphic transformation. So that means polymorphic means different types of crystal structures. So whatever the ferrite is there, this ferrite will experience a polymorphic transformation to FCC, and this is called as a austenite temperature, which is called as a gamma iron at 912 degrees centigrade. So all these things you have to remember very carefully. So how this is being transforming from one phase to other, one type of crystal structure to other crystal structure, while changing the temperature scale. Okay, so initially it was a ferromagnetic, that is the ferrite type of thing, which is having a BCC type of crystal structure at room temperature. Now this same ferrite slowly, when increase the temperature to 912 degrees centigrade, so this ferrite is transforming slowly to the austenite scale, that is having the FCC type of crystal structure. So from BCC to FCC, and ferrite to austenite, it is being converting. So from alpha to slowly at 912 degrees centigrade, it is shifting to the gamma iron. Okay, so from alpha to gamma, from BCC to FCC. So this is again the second type of thing, the phase structure you can observe here, that is the phase centered cubic structure. So from BCC to FCC, from body centered cubic structure to phase centered cubic structure, it is being transforming at 912 degrees centigrade from room temperature. Next, what are the austenite is there, that is the gamma. It will persist up to 1394 degrees centigrade. So up to 1394 degrees centigrade, there is no change of that austenite, that is the gamma iron. So after reaching that 1394 degrees centigrade, what is happening? Slowly it is being converting into a delta type of thing, which is called as a ferrite at 1394 degrees centigrade, which is called as a delta ferrite, gamma iron, alpha iron. Okay, at 1394 degrees centigrade, which is having again the BCC type of crystal structure. So it is a cycle thing. So from BCC to FCC, again from FCC to BCC. And what are the temperature scale you can observe? Initially at room temperature you have a BCC. Slowly if you increase to 912 degrees centigrade, it is converting from BCC to FCC. And again if you increase the temperature from 1394 degrees centigrade, from FCC, again it is converted to BCC. So this is the different changes of crystal structure you can observe during the heating process of this pure iron. So this is the third thing you can observe here, from gamma to delta. So BCC to FCC, FCC to BCC. So this is the third. So after 1394 degrees centigrade, what is happening? Then the delta ferrite melts into liquid. So from this point after crossing this 1394, when it reaches to 1538, okay, it start melting with the liquid. So up to this 1594 degrees centigrade, 1539 degrees centigrade, it won't melt with the liquid. So after crossing the temperature of 1538 degrees centigrade only, it can try to melt with the liquid. So from this figure or from this phase diagram, what can we get the information means? We can get the information that the liquid, the pure iron melts at 1539 or 1538 degrees centigrade. So at that point, you can get the melting temperature of the pure iron. So this is how you can get the information of what is the melting temperatures of the pure iron and what is the different types of crystal structures you can observe at different types of interval or different temperature scale. So all these things you can observe with the help of these phase diagrams only. So that's why the phase diagram is very, very important while describing or while characterizing any type of material. So these are the three formations or these three formats of the FCC or BCC and again the BCC. So this is the structure you can observe. So initially it is the first stage of the BCC ferrite at room temperature, that is at normal 28 degrees centigrade. Slowly this second state at 912 degrees centigrade, it is converting into austenite. And again at third point around 1394 or 1354 degrees centigrade, you will get again the BCC. So this is the transformation of the different types of crystal structures you can observe at different interval of time period. And so this is the exact phase diagram of the iron carbon phase diagram. Now you can clearly observe. So we are considering this phase diagram into two parts. So first part up to what percentage we are considering? Up to 6.67 weight percentage of carbon. We are considering the steel. Steel we are considering up to 6.67 weight percentage. If you cross, that is beyond 6.67 percentage of carbon, if you consider, so it is not under steel, so it will be under graphite. This we are not considering, only we are considering up to 6 point. That's why if we see here, this is 6.67 percentage. So up to this point only we are considering the phase diagram of the iron carbon phase diagram. That's why this iron carbon phase diagram is very complex. When you compare with any other type of phase diagram, so this phase diagram is very, very complex and is having different types of crystal structures observed during the cooling process. And also, if you increase the composition of the weight percentage of carbon, again it converts to other type of steel. So what are the steel we are considering? We are considering up to 6.7 weight percentage of carbon only. That's why we are restricting our phase diagram from 0 to 6.7 weight percentage. So here you have two scales here. Hypoeutectoid. So hypoeutectoid from 0 to 0.08. Hypoeutectoid. Hypereutectoid means from 0.8 to 2. From 0.8 to 2. And eutectoid means 1 point from here to here. This is eutectoid or eutectic temperature. So like this you have eutectic. Before eutectic temperature you have hypereutectic, and higher than the eutectic temperature is called hyper. So in the name itself you have hyper, hypo and eutectic. So these three are the different types of temperatures you can find out in the help of the phase diagram. So it is easy for us to describe what is the hyper-eutectoid, and eutectic temperature based upon the values of the weight percentage as well as the temperature scale. Now initially we have the ferrite thing. What are the thing we have seen here? It is the alpha tank at room temperature. Slowly this alpha is converting into austenite. Okay, and after reaching to the this melting point, okay, it starts with melting with the liquid. So that's why you have complete liquid zone at this point. So you have a ferrite, that is the iron carbide here. Slowly austenite, and austenite again you have austenite and iron carbide you have here. So here it is ferrite, initially ferrite, that is the alpha, and then austenite. Okay, so all these things, alpha and delta ferrite. Okay, so these are the three transformations, 1, 2, 3 transformations of the phase diagram what you can observe. Now everything you can clearly observe from the phase diagram. So from 0 to 0.83 weight percentage is called hypoeutectoid. So what is the hypoeutectoid? Temperatures means from 0 to 0.83, sorry, 0.83, it is called hypoeutectoid. Next, hypereutectoid means 0.83 to 2%. So all these are in hyper percentage. Hyper. Now in between hypo and hyper you have a eutectic. Eutectic temperature. So that is how you can get the information of these three variables from the help of the phase diagram. And also what are the types of compositions you are available at each stage. And also what are the different types of phases, or what are the different types of compositions that are available at each phase with respect to the temperature can be observed with the help of the phase diagram. So earlier it was in the ferrite state and in the room temperature. Slowly this ferrite is converting to austenite at 12 degrees centigrade, and slowly this ferrite from austenite to again the perlite or delta ferrite, it is converting at 1394 degrees centigrade. So like that you will get all the informations of these changes of phases or changes of the composition with respect to the composition as well as the temperature from the help of the phase diagram. So what are the different types of phases present at each phase of the iron carbon phase diagram? First one, here you have the Fe3, that is the iron carbon phase diagram, is characterized by 5 individual phases. So totally you have 5 individual phases in this phase diagram, that is the iron carbon phase diagram. So first one we are seeing at the alpha ferrite, which is having a solid solution at BCC. So we have seen that at initial temperatures, or that is the room temperatures, we have the BCC type of crystal structure, that is called the ferrite, alpha ferrite. Okay, so this is the stable form of iron at room temperature. So this is very, very important. So at what temperature? At room temperature. At room temperature, pure iron is stable, and which is having a alpha ferrite and BCC type of crystal structure. So that is the first point. Second point is the maximum solubility of that solid will be 0.028% of carbon. So what is the maximum solubility limit? Means the maximum solubility limit of the carbon is 0.028%. And the transformation starts from that point, that is the BCC to FCC, that is the austenite at 912 degrees centigrade. So from room temperature, from the BCC, it is slowly converting to austenite at 912 degrees centigrade. So that is the first one you can observe. So this is the category of that observation of the ferrite. So what is happening here? So this is at BCC. So this BCC is slowly converting into FCC from ferrite at 0.02 to a 0.768 percentage. At 912 degrees centigrade, it is being coming. So at this point, we are getting this conversion of the ferrite to austenite. And again, slowly we are seeing this at 2.4 percentage. It is converting to austenite, and again it's reaching this point, and we are getting the melting state. So this is how you will get the melting point of all those things. So what are the invariant reactions we are observing at each point of the phase diagram? Means first one is the pertectic reaction. So what is pertectic reactions mean? At 1495 degrees centigrade, that is at 0.168 percentage of carbon. So what is happening? You are getting the austenite. How we are getting this austenite? This delta ferrite with liquid. Okay, with the delta ferrite with liquid, it is completely converting into the austenite, that is the gamma iron. So when a solid plus liquid both are there, when you're trying to cool or heat the system, it will convert into complete austenite thing. So that type of reaction is called as a pertectic reaction. This reaction can be observed at 1495 degrees centigrade at 0.168 percentage of carbon. Then the monotectic reaction. So this is also at 1495 degrees centigrade, but what is the change in the composition here? 0.51 weight percentage of carbon. So there is a difference between these two. Of course, this and this are same, but the composition if you observe here, so per pertectic reaction you have 0.16 weight percentage of carbon, and coming to the monotectic reaction you have 0.51 weight percentage of carbon. And here also, what are the liquid is there? So this liquid will, when you heat or cool, you will get converted into one liquid plus one solid, that is called as a austenite. Liquid plus gamma iron, you will get into austenite. So that is the monotectic reaction. The third one, eutectic reaction. So this eutectic reaction you can observe at the 1147 degrees centigrade at 4.3 weight percentage of carbon. So at 1147 degrees centigrade at 4.3 weight percentage of carbon, you are getting this cementite formation. So how we are getting this cementite? The liquid, when you heat or cool, so what are the thing you are getting? It is in the form of two solids, that is the gamma iron and Fe3. So two solids when you getting at 1147 degrees centigrade with 4.3 weight percentage of carbon, then that type of system is called as a eutectic reaction. The last one is eutectoid reaction. So this eutectoid reaction we can get at a temperature of 723 degrees centigrade at a composition of 0.8 percentage of carbon. So here the gamma iron, whatever the gamma iron is there, so when you heat or cool this gamma iron, it converts into alpha ferrite as well as cementite. So this is called as a perlite. So this is how you will get the different formations or the different transformations of the phases when it starts varying with different temperatures and with different compositions along the phases when we are converting. So during this transformation, so what are the transformation temperatures we can observe here? First one is called the A1. So A1 is nothing but the temperature at which the austenite begins to form during the heating process. So when you heat the pure iron, what is happening? At some point of temperature, the austenite begins. So that transformation temperature is called as a A1. So next A2 is what? The temperature at which the iron becomes non-magnetic. Whenever the iron is becoming into non-magnetic, then the type of temperature is called A2. Then A3 is the temperature at which the transformation of iron into austenite is completed during the heating process. So when you heat the pure iron, what is happening at that temperature point? There is a transformation of the alpha iron into austenite. Then this temperature is called as a A3. And last one A4, temperature at which the austenite transforms to delta ferrite. So all these temperatures, what are the A1, A2, A3, everything we are getting the values or the information from the help of the phase diagram. That's why the phase diagrams are very, very important. And coming to the last one, A4, AM, the temperature at which the solution of the cementite in austenite is complete. That means completely the pure iron is being mixed with the liquid state. Then that type of temperature is called the AM temperatures. So like this, you can easily distinguish what is happening at each interval of temperature, what is the type of microstructure it can have, what type of phase structure it is having, what type of, how much of composition does this iron does have. All these things can be observed, or we can get the information from the phase diagram. And what are the phase transformation? Under the equilibrium conditions, pro-eutectoid ferrite will form in iron carbon alloys, which containing up to 0.8% of carbon. So that is one point you can observe. And the reaction occurs at 912 degrees centigrade in the pure iron, but it takes place at 723 in Fe3C alloy. So this temperature scale is very, very important. So how it is being converting from the ferrite to austenite or ferrite to perlite means all these things we can get with the help of the temperature scale. So from the initial state of room temperature, it is converting to austenite ferrite or austenite with the temperature of 912 degrees centigrade of Fe3C alloys. The perlite, what are the perlite you have? So this is the combination of the nucleate and the ferrite compositions. Okay, ferrite and cementite, which is the combinations of these two, which is called as a perlite. And it is very clear that they can also be associated with the both pro-eutectoid ferrite as well as the cementite. So combination of the ferrite and cementite is called as a perlite. In commercial steels, the perlite nodules can nucleate on inclusion. So you can observe clearly what is the structure, microstructure view of each type of element. By seeing the crystal structure, you can tell what type of material it is. So austenite will look like this, and cementite you can observe some nucleus like this. The ferrite, again, it has different types of things. So by seeing through the microstructure, you can easily tell that what type of crystal structure you have, or what type of material we are using for the different applications. So perlite means, so it is a alternate layers which are being formed with the ferrite and cementite. So what is the black thing you are seeing? So that is called ferrite, and the white patches you can see as the cementite. So this is how you can differentiate between the materials with the help of these phase diagrams also. So these are some of the transformations of the phase diagrams during the cooling process or the heating process at each point. So this is the, if you neglect those phase crystal structures, it is the nothing but the phase diagram. So during this phase diagram, if you draw lines at the eutectoid temperature, hypoeutectoid and hypereutectoid lines, you will get the different transformations of the phases. So earlier it was completely of ferrite. This is ferrite, and here you have the ferrite as well as austenite, and you have completely of plus delta plus gamma. So this is alpha, delta, alpha. So like that, at each point of the phase diagram, you can see clearly how there is a transformation of the phase diagrams at each point. So all these things can also, we can get the information from the help of the phase diagram. So that's why the phase diagrams are very, very important in drawing these structures, in identifying the what type of crystal structure we have, and what is the composition of each type of crystal structure can also be inferred from the help of the phase diagram. And this is how you will get the eutectic reaction. So at that point, at this point, if you observe, so this point is called eutectic temperature point. So at this point, if we observe what is the different types of crystal structures we are getting, so you have to draw a line which passes through this temperature. And if you see at this point and at this point, you have here combination of alpha plus Fe3, that is the cementite. Completely it is called as a perlite. And here you have the complete 100% of gamma austenite. So this is the phase diagram, phase transformation in terms of the eutectic or eutectoid reaction. So when you a solid, when under cooling or heating process, it forms into two solids, then the type of reaction is called eutectoid reaction. So when cooled slowly forms in perlite. So this transformation is transforming from austenite to perlite. So perlite is the combination of again the ferrite as well as the cementite, that is Fe3 and alpha. And you have some different classifications of steels and cast irons. So based upon the compositions, again, you can easily classify what type of steel it is. So iron carbon alloys that contains between 0.008 to 2.14 weight percentage of carbon, these are classified as steels. So what is the range of the steel in which the carbon content is present? Means 0.008 and 2.148% of carbon content if it is present, then that type of classification comes under steel. Now hypoelectric steels means 0.008 to 0.8%. Hyper means 0.8 to 2.1%. So this is how you have the difference in the hyper and hypoelectric based on the composition of the carbon content. Now cast irons, how you are classifying means beyond that composition of the steels, that is from 2.14 to 6.70 weight percentage, then that type of classification comes under the cast iron. So like this, we'll have different types of classifications of the steels as well as the irons. And again, in this case also you have the hypoelectric cast iron and hyper. So hyper means 2.14 to 4.3 weight% of carbon, and hypoelectric means 4.3 to 6.67 weight% of carbon. So this is the classification of the steels as well as the cast iron. So this we will discuss in the next coming sessions. What are the different classifications of steels and what are the different types of ferrous and non-ferrous elements. So how we are getting all this information means everything we are getting the classification of steels or classification of cast irons or classification of the eutectoid, eutectic and per-eutectic, all these invariant reactions, all these things information we are getting the information from the phase diagram. That's why this phase diagram is very, very important. At the same time, it is very, very complex to understand the concept of the iron carbon phase diagram. And this is the, of course, the hypoelectric steel where you can see the crystal structure. So it will looks like this. So dark spots are called the carbon, and white patches will look like the perlite and some austenite things. In hyper, completely of dark thing. Why? Because there is a high percentage of carbon content present at this junction. And if you see the microstructure of each austenite or ferrite, all the type of from the changes from the BCC to FCC and then FCC to BCC, that means the conversion of the microstructure or the changes in the microstructure or the development of the microstructure, if you observe at each point of interval in the phase diagram. First you can see the austenite, so it will look like this form of austenite when you see through the microscope. And ferrite, again the alpha components, so this is the microstructure of the ferrite. And all the things we are studying. So what is the ultimate importance of this phase diagram means solubility of carbon in iron carbon alloys can be identified. Various phases and microstructures which are present can be identified with the help of the phase diagram. Transformation temperatures from various carbon compositions in the Fe3C system can be identified. Invariant reactions and the classification of steel and cast irons can also be inferred from all these things. So these are the main important things what we can get the information from the phase diagram. So that's why the iron carbon phase diagram is very, very important in classifying the what type of steel or what type of cast iron is, and what are the how many invariant reactions are there, and what are the developments of the microstructure while transforming from the different times of different temperature scale. And also you can get the solubility of the carbon in the iron carbon alloy system, and also what are the different phases present and what are the microstructures are present in the phase diagram can also be get from the iron carbon phase diagram. So this is the very, very important topic in the materials engineering, that is the iron carbon phase diagram. So these are some of the references books where you can get the information about the iron carbon phase diagrams. So first one is the Introduction to Physical Metallurgy by Sidney Hefner, and the second one is Essential of Material Science Engineering by Donald. The third one is Material Science and Metallurgy by Kodigiri, and the last one is Material Science and Engineering by William Cashler. So these are the references books where you can get the information of the iron carbon phase diagram. Thank you for the session.
Like, share and subscribe. Hit the bell icon for more updates.